Hi, everyone. Welcome to lecture 7 of CS466. And today we're going to talk about some algebraic techniques in computer science, okay? And those are going to be like fingerprinting and how to verify polynomial identities, and also the prelude for parallel algorithms for matching problems, okay? So, all right. So, and today what's the outline? So we're gonna first, ask the usual question: why should we bother having algebraic techniques in computer science? And isn't deep learning and everything, machine learning, like the best thing ever for everything? And the answer is, of course, not. And then we're going to see the first example, which is fingerprinting, right? And then we're going to talk about the main problems that involve, for today, that will involve algebraic techniques, which is the polynomial identity testing. And then we're going to see an application of identity testing for randomized matching algorithms. And then we're going to talk about a little bit about isolation lemma. Okay, so all right. So let's get going. So why should we use algebraic techniques in computer science, right? So it's really hard to overstate the importance of algebraic techniques in computing. Okay, so for instance, it's a very useful tool for randomized algorithms, as you saw in hashing, and the hashing techniques that we have were algebraic, right? And in today's lecture as well, you're going to see the importance of algebraic techniques in randomized algorithms. It's also important in parallel and distributed computing, and you're going to see a little bit today in the parallel setting here and in lecture 21. And it's also used in interactive proof systems, okay, in a key way. We're going to see a little bit of that in lecture 23. And it's also used in efficient proof or program or software verification, okay? So this has also application in hardness of approximation of algorithms, has applications in the blockchain, so it's being used actually in practice today as well, and also used in zero knowledge proofs. Okay, and more examples is, well, cryptography. You have a lot of algebraic techniques in cryptography as well, and in coding theory as well. Okay, so you can see that those algebraic techniques appear everywhere in a flavor or another. So it's really hard to overstate the importance of them in computing. Okay, so all right, and now let's just see one application of a technique that's called fingerprinting, right? And you already saw kind of hashing is a type of fingerprinting. And the first application here is verifying string equality, right? So suppose that we have Alice and Bob, and each of them maintain the same large database of information, right? So think of each of them, like think of Alice and Bob, each of them being like a server of a huge company, okay, that has like massive data, right? So this company has two servers, like in two locations, and they would just like to check if the databases are consistent, right? Like, so if they have the same information in their database, right? So, okay, well, what is one way to do it? One way to do it is, let's say Alice can just send all of her database to Bob, and then Bob can go and check each entry and check that the entries are exactly the same, right? But transmission of all the data is, of course, expensive, right? So, and here we're in the communication complexity computational model, which we may talk about like later in the course, okay? But this is where like transmitting data, you should think of it as a very expensive operation, right? So you definitely don't want to do that. So, okay, so we know it's not feasible to send the entire database. And now suppose that Alice's version of the database is given by bits, right? Just for simplicity, like the bits are A1 up to AN. And of course, the order of these bits matter, right? Because the databases like are ordered, are stored in order, right? And suppose that Bob's version is B1 up to Bn, right? So they both have like these databases with n elements. And now they want to check if those databases are the same. So, all right, so to deterministically, okay, if we want to do this deterministically, so this deterministic consistency check requires Alice and Bob to actually communicate the n bits, okay? Otherwise, you should think, well, if Alice and Bob don't communicate all of their bits, right, the adversary will know how to change the database on how to make it fail, okay? So there's a way of making this formal, but, just you can think about it just intuitively, right? Like if let's say the naive protocol is that we communicate like pieces of our database. And if we don't communicate n bits, then there's one bit of information that's left. And this bit can be changed by an adversary. Okay, so that's kind of the intuition. So, all right. And so then we definitely don't want to do a deterministic consistency check, right? So it's impossible for us to do it without communicating like most of our like our entire database, right? So here's what we do. We're going to introduce randomness, right? And the fingerprinting for the rescue. Okay. So, all right. So, and just to, just emphasize again that you can see here that as we have been seeing in the class, the importance of the computational complexity model that you have. Okay, it's important to give you like what are the resources that are most scarce and what is the thing that we need to prioritize when devising algorithms, right? So this is the communication complexity setting, and we are in the randomized algorithms, right? So we don't want an algorithm to work all the time. Again, we are gonna want an algorithm just works with high probability, right? So, all right. So, and the verifying the database is equivalent to verifying if the two strings are equal, right? Because I need to compare A1 with B1, A2 with B2, A3 with B3, and so on, right? So how do we check that these strings are equal? Remember, each AI and BI are bits. So what are we going to do? Well, here's a fingerprinting mechanism, right? And if you think of what is a fingerprinting mechanism, a fingerprinting mechanism is essentially the same thing that tries to emulate like our fingerprints, which are like unique with high probability, right? So we're trying to create a scenario where different strings with high probability get mapped to different objects, right? So, all right. So what is our mechanism here? The mechanism will be the following. Let's consider A to be the integer, okay, which is given like when given in binary, okay, it's A in binary has the representation A1 up to AN, okay? Does that make sense? So we're just representing A in binary, okay? I think probably the way I wrote here, the binary representation of A would be AN minus 1 all the way up to A1, right? And B, I'm just representing it by an integer. And again, such that the binary representation of B is Bn minus 1 all the way up to B1. Does that make sense? So I'm just writing those two integers, A and B, which are integers now, right? And the strings are their binary representation. So, okay, now here's the thing, right? Let's say that the function fp of x, okay, which just takes an integer x and take its residue modulo p, right? Let's say that this is our fingerprinting function for some prime p, okay? We have to choose the prime p, okay? So, because certainly, we know that like A and B, I cannot send A, like Alice could not send A to Bob because sending A requires her to send like an n-bit integer, right? So we certainly don't want to send the whole bit. Does that make sense? Because these integers, so these integers are like n-bit integers. So we cannot send those bits across the channel. We have to make those like integers to be much smaller, right? And this is exactly what our fingerprinting function will do, right? If I just take x mod p, right? This will be now, like the answer will be something of log p bits, right? And hopefully we want to make log p much less than n. Does that make sense? Okay, so, all right. So here's the protocol, okay? So the protocol will be the following. So Alice will pick a random prime p, and Alice will send both p and the fingerprint of her database to Bob, right? So we're sending the prime plus the fingerprint. Okay? So, and then after that, Bob is just going to check, because now if Bob knows the prime, Bob knows how to compute his fingerprint. So Bob is going to check whether the fingerprints are the same, right? And then he will send 1 if the values are equal, or 0 otherwise. Does that make sense? So that's the protocol that they're doing, okay? Now, what are the total bits communicated, right? The total number of bits communicated in this protocol, which is the total communication they had, is exactly O of log P bits, right? And why is that? Because, well, Alice is going to send P and FP of A. So this is like roughly 2 log P bits. And then Bob just communicates 1 bit. Correct? So now you can see how we went from having to communicate n bits to only communicating log P bits, right? And now we have to, but now we haven't analyzed what is the probability of success of this algorithm, right? And that will have to do with this, with the size of the prime that we're going to pick, right? That we have to pick, okay, of this log P. So let's continue. Okay, so here's the thing. Let's just prove some more things about this, right? So if their databases are the same, right? So if the string A1 up to AN is equal to B1 up to Bn, this protocol is always right, right? Bob will always reply 1. Does that make sense? Just because the integers A and B are different. So if the databases are the same, there's nothing for us to worry about. The only thing we need to worry about is, well, okay, what happens when the bits are different, right? Because if this algorithm is almost always wrong, like let's say if it's wrong with half of the probability half of the time, we might as well not even communicate a prime, right? We might just each flip a coin and say, okay, like our databases are the same or not, right? So we have to show that when the databases are different, then with high probability, this protocol will actually output 0, right? So that's what we want to check. Okay. So, all right. So we know that if A1, if the strings are different, then the integers A are different from B, right? Just because they're the binary representations. So, okay. Now, the question that we should ask is, for how many primes? Because remember, we can pick our prime at random, right? So for how many primes can the fingerprints, when assuming that A is different from B, right? The fingerprints will give the same value, right? For how many primes can this happen, right? And the answer is this, right? So if a number m, suppose that a number m is between -2 to the n and 2 to the n, then the number of distinct primes that divide m is less than n. Okay, this is the lemma we need. Okay, so let's just first prove this lemma, right? The proof is quite easy. So each prime divisor of m, so let's write m as, let's just factor m, right? So it's p1 to alpha 1, p2 to alpha 2, up to p, t to alpha t, right? So suppose that m has t distinct prime divisors. So these are all distinct, right? So, and the alpha i's are greater or equal to 1. So in particular, we know what? We know that each of these primes, so each prime is greater or equal to 2, right? So m, first of all, is equal to p1 alpha 1, p2 alpha 2, pt alpha t, which is greater or equal than just the product of the pi's, I equals to 1 up to t, but each pi is greater or equal to 2. So this is 2 to the t. Actually, it's right? If t is bigger than 1, then we know that this is bigger than 2 to the t. Does that make sense? So in particular, right, we know that this happens, but m could be negative, right? So let's just say that m is the absolute value of m. So, all right, so we know that the absolute value of m is greater than 2 to the t, right? But remember, we know that the absolute value of m is also less than 2 to the n, which implies that t is less than n. Does that make sense? So if a number is between -2 to the n and 2 to the n, then the number of distinct primes dividing m is at most n, right? So we have this lemma now. Is that clear? Okay, so then, all right, so now let's see what's the probability that f, like, for how many primes, right? Like, will the fingerprinting be equal, right? So the thing is, if you notice, what is the fingerprint function? We know that FPA, right, is just equal to A mod P, and FPB is equal to B mod P. So then FPA is equal to FPB if and only if A minus B is congruent to 0 mod P, which is equivalent to P divides A minus B, correct? Okay, so then now, now what do we have? Well, what is the, but now let's just measure A minus B. So what is A minus B? We know that each A and B, they're both integers, like non-negative integers. And we also know that they're n-bit integers, right? So they are both between 0 and 2 to the n, which implies that A minus B, right, is less than or equal than 2 to the n, and also greater or equal than minus 2 to the n. Correct? So A minus B is a number between minus 2 to the n and 2 to the n. So in particular, we know that at most n primes divide A minus B. Correct? Okay.
Yeah.
Joey, I have a question.
I just said yeah, correct.
Oh, okay, great. All right, so then we know that this protocol will fail for at most n choices of B, right? So, all right, so now what do we do? Well, we just have to make sure that among, like, because Alice has to make this random choice of B, right? So all we need to do is that Alice will not choose a bad prime with high probability. Does that make sense? So, all right, so what do we do, right? Well, we have to now invoke the prime number theorem that says there are m over log n primes among the first m positive integers. Does that make sense? So that's just the prime number theorem, right? And now, so if we choose our prime p, okay, among the first tn times log tn primes, what is the probability that we're going to fail? The probability that FPA is equal to FPB. And remember, here we're assuming that A is different from B, right? Like with A different from B is less than or equal to what? Is less than or equal than the total number of bad primes over the total number of primes that I'm choosing, right? Like number of primes I can choose from. Does that make sense? So in particular, what is our probability of failure? Our probability of failure is exactly O of tilde of 1 over T. Right? So this is the probability of failure. So if we want to make this probability really small, we can just take, for example, T to be n, right? And then we have that our, like, if the databases are the same, we're always going to output the correct answer. But if databases are different, with probability 1 over n, we're going to output a bad answer, right? Does that make sense?
I'm confused. What is T?
T is a parameter that you can pick. Right? It's just the parameter that will tell Alice, pick a prime number, like pick a random prime number among the first, like, you know, Tn log Tn primes. Does that make sense?
Right.
That's just the parameter. So, all right. So then we have this probability, right? And then we can choose T. So, okay. So then what is the number of bits that we're going to send, right? Because now the thing is, suppose that I pick P among the first T and log Tn primes, right? So if you remember, oh, sorry, I think here what I meant is the first, like we want to pick among the first integers, right? That's why we're using the, like, and then we can use the prime number theorem. So sorry, this should be integers, right? So let me put integers here because we're invoking the prime number theorem. Integers. So we pick P among the first Tn, log Tn integers, and then we just need to pick our prime from there, right? So we know how many primes are there. There's many primes. Now, if P is chosen among the first Tn log Tn integers, what is the bit complexity of P? How many bits will P take? Well, we know that the log P, right? Because we're picking among these integers, we know that P is less than Tn log Tn, which means that the number of bits of P is less than or equal than log T plus log N plus log Tn, right? But this log is pretty, you know, yeah, we don't care about it, right? It's a low order term. So in particular, we know that log P, if we pick like log P is equal to O of log T plus log N. So if we pick T equals to N, right, we know that log P is big O of log N. So instead of sending N bits, right, which is the deterministic protocol, this protocol that we have actually sends O of log N bits. Does that make sense? Great. So then, okay. So then this is the how to verify string equality with much less communication, right? Now we need to communicate O of log N bits as opposed to communicating N bits. Okay. So you can see the exponential improvement here by using this technique. Okay, so now this is the first part of the lecture. So let me just stop here. And do you